Okay, by this time you're probably sick of this particular chart, but hopefully you've got a copy of it in front of you because we're going to need it a lot today. And remember, you're allowed to use it during your final. Okay, and matter of fact, you want to have it for the final. It has a lot of information you're going to need during the final itself. So let's practice the Nernst equation. So I've given you two half reactions. So I want to give you a moment to see if you can write the overall spontaneous reaction. Now remember the name of the game. In fact, if you look at these two half reactions, notice they're both reduction half reactions. So obviously you're going to have to switch one around, and you always want to switch it around so you get a positive E0 because that guarantees it'll be spontaneous. Okay, and here's the result that I got when I did it. So it looks like what I had to do is I want a positive value. So if I switch the bottom one, I'll be adding two positives together. Okay, I got to make sure the electrons cancel out. So it looks like I have to triple the top one. Okay, so that's going to give me the 3C plus 4s. Okay, and let's see, so it's got chromium positive, or chromium 0, when I switch the bottom one around. Okay, and I'm going to get 3 cerium plus 3s and the 1 chromium. Now remember, even though I tripled the half reaction, the voltage doesn't change because remember, voltage is push per electron, so you just blindly add the two together. You don't double or triple anything, so that would be the E0 there. Okay, let's call that problem A now. So we now have the voltage. Remember that standard voltage means everything's at 1 molar concentration. Now, problem B, let's change the situation by changing the concentrations. And the goal now is to find out what the new voltage will be. Now, I always think it's kind of fun to kind of guess how the answer is going to turn out. So, for example, I noticed that I made the reactant 2 molar. Okay, and think in terms of Le Chatelier's principle, that's like going from 1 molar to 2 molar. You're making it more. That's like a stress, so it should shift the system to the right, giving you more voltage. Okay. Notice I didn't change the chromium solid. Solids can't change their concentration. That's why that one is left blank. Okay, cerium plus 3, I've made that 0.01 molar. Okay, so now that's like a less in the Le Chatelier's principle, so that's going to help it go to the right. And the same thing on the last one. So my guess is, wouldn't you agree, the voltage should go up. So let's see how the calculation works out. Okay, so remember how the Nernst equation goes. The voltage is equal to the standard voltage, so I copy the plus 2.35 volts again, minus 0.06 divided by N. N is the number of electrons being transferred, and if you go back, look at the half reactions, N is the 3. Then the log of products over reactants. So the products are cerium plus 3. Notice it's got to be cubed. The chromium, 0.01 to the first power, divided by the reactant, which is 2 molar to the third power. Okay. And I think I'll try my calculator to see if it's going to work for me this morning. So let's see, I've got 0.01 times 0.01 times 0.01, so that's the cube part, times another 0.01, divided by the reactant C. 3 cubed is 8, so divided by 8 equals, I'm getting a very, very small number, too many zeros to count, I'll hit my log button. I'm now getting negative 8.9, and that's going to be added to the positive 2.35, so plus 2.35, and I get a ridiculous answer, so I did something wrong, but anyway, the answer would be positive 2.53. So the voltage did go up a little bit. Okay, here's problem C. Now again, let's see if we can guess how the answer is going to turn out. Let's see, so I made the starting material less than 1 molar, so that's going to hurt the voltage. That's like a less on the left. So that's going to hurt the voltage. The next one, the cerium plus 3, I made 0.85, and that's like a hole. That'll help the voltage because it'll want to go to the right. And then I made the last one 1.2 molar, which ought to hurt the voltage. So what do you think? The first one will hurt, help, hurt. Okay, so a little bit hard to predict. What do you think? Well, let's see how the voltage turns out. Okay, so plugging in the Nernst equation, the voltage is equal to, again, the standard voltage, okay, minus 0.06 divided by the number of electrons being transferred, log of products over reactants. So the products are 0.85, but it's got to be cubed because of the 3 exponent, okay, and 1.2 to the first power, okay, and the reactant 0.35 has got to be cubed. Okay, let's see if I can have better luck on my calculator this time. So let's see, I've got 0.85 times 0.85 times 0.85, okay, times 1.2 divided by 0.35, 3 times divided by 0.35 divided by 0.35. Okay, I get an answer of, wow, 17.1. I'll hit my log button. Okay, and then it's got to be multiplied times a negative 0.02, so 0.02 negative. Okay, and this gets added to the E0, so plus 2.35, and I get an answer of 2.325, which adds up to 2.33. So it looks like the voltage did go down a little bit. The standard voltage was 2.35, and this became 2.33. Okay, so hopefully you're pretty good. You feel pretty good about using the Nernst equation at this particular point. Okay, are you seeing the Berg special? The Berg special as we came up on your screen, okay?
Yes.
Okay, good. Okay, now here's how the Berg special goes. Okay, so here's the reaction I've given you. And now I want you to use your half reaction table to find which the half reactions you need. Okay, so iron 2 to iron 3, or iron 3 to iron 2, you find on your chart. Let's see, where is it? It's about a quarter of the whole chart. Yeah, there it is, iron 2 to iron 3. It looks like I had to reverse it to get iron 3 on the left-hand side. Now, why did I double the whole thing? Okay, because notice the balance equation has 2 irons in it. Okay, now notice the hydrogen half reactions right in the middle of the whole chart. It's kind of marked for you. Okay, now add up the 2 half reaction E0s to get the total E0. Okay, so notice that the iron one is a flip of what's on the chart, so I had to flip the sign to make it positive, and the hydrogen is a 0. So add the 2 together, and the E0 is plus 0.771 volts. Okay, now I'd like to change the concentrations, which is always kind of fun, because then we'll change the voltage. So I'm going to make the iron 0.3 plus 1.50 volts. Notice the hydrogen, it's a gas. When it comes to gases, you don't use molarity, you use their pressures in atmosphere. So if I give you a problem, I would, and it has a gas, I'll give it the pressure in atmosphere. Notice the iron plus 2 is 0.001 molar. Now here's the weird thing. For the hydrogen concentration, I didn't give it to you. I gave you pH, the dirty guy, okay? So let's see how this all plays out in the Nernst equation. So the voltage of the cell will be the standard voltage, just copy that, okay? 0.06 divided by, why is it 2? Yeah, if you look at the 2 half reactions, they're passing 2 electrons, it's a passive 2 electrons. Okay, the log of products over reactants. So the first product will be the iron 2, that's 0.001, gotta be squared. Now, you can't put pH in, you've gotta put hydrogen concentration in. And it's been a while, I know that, but remember, if the pH is 5, it means the hydrogen concentration is 1 times 10 to the minus 5, and it's gotta be squared because of the balance equation. Okay, and the reactants are 1.5, so it ought to be squared 0.5. Okay, and I get an answer of 1.25. Let's see if I can really get that again on my calculator. So let's see, I like to do the log term first. So I've got 0.001 times 0.001 times 1 EE5 minus 2 times 1 EE5 minus divided by 1.5 times 2 times 1.5 divided by 1.5 divided by 0.5. So I've got the fraction is, wow, 8 times 10 to the minus 17, something like that. Anyone verify that? Anyone doing this along? I hope you practice on your calculators with me, by the way. I'll hit my log button. I get something like negative 16. Then I have to multiply it times 0.03, change the sign, equals, I've got 0.48, and that's got to be added to the E0 plus 0.771, and I get an answer of 1.25 volts. Okay, here comes Super Killer. This is the one I've been building up to. This is really the Berg special. Now, at first glance, it looks like it's pretty easy. I've made everything 1 molar, 1 atmosphere, then that makes the math easy. But wait a minute, I didn't give you the pH. But I did give you the voltage of the cell. So the hope of this is maybe we can use this electrochemical cell to actually get the pH of the system. Okay, so here we go. Now, first of all, I'm not going to plug in some numbers for the moment. I'm just going to use letters. So the voltage of the cell we know, but I'm just going to use E for the moment. Okay, and same thing, we know E0, but again, we'll put the numbers later. Okay, times or minus 0.06 divided by 2 log of, and here's all these ones that I gave you, and the hydrogen ion concentration. Okay, so getting all the ones out of there, the equation looks like this, much simpler. Now here's a cute little trick you might remember from logs. You have the log of hydrogen concentration squared. Remember, you're allowed to bring that 2 out in front of the log button. Okay, and then it cancels with the 2 over here. Okay, so that simplifies it even more. So look at that math again. So the log of hydrogen concentration squared at the same thing as 2 times the log of the hydrogen concentration. So now the 2's cancel out. So now the equation looks like this. Okay, now I'd like to do a cute little math trick, and it goes like this. You see that negative in front of the 0.06? I'm going to change that to a positive and put the negative in front of the log of the hydrogen concentration. Now, why in the heck would I want to do that? Can you tell me? Because minus the log of the hydrogen concentration happens to be equal to, I marked it in red, da-da-da-da, pH. So now we got pH in the equation. Now, on the final exam, if I ask you to solve for pH, you have 2 choices. You can just solve for hydrogen concentration and then get minus the log of it later. Or if you're clever enough and you get pH right into the equation itself, it makes your math a little bit easier. Now, I want you to take a good hard look at this equation because it satisfies the equation of a line. Okay, so the voltage of the cell would be a variable. That's like Y. Okay, the standard voltage will be a constant. That will be like the Y0. The slope will be the constant 0.06, and the X will be the pH. Now, the first person to discover this was a Caltech chemist by the name of Beckmann. And Beckmann became rich and famous by, he actually invented the pH meter, which I'll show you in a moment, and he actually invented a whole company on electrochemical instruments. And it was all based, his first thing was discovering that this actually equation follows the equation of a line. Okay, so anyway, here's the equation of a line. So here's the equation you saw before. Okay, and here it is plotting this. Okay, so here is Beckmann's first pH meter. Essentially what he did is he sold people this giant box. This giant box is nothing more than a voltmeter. And then he sold them a chart. The chart is the chart you see above. Okay? And so what they do is they measure the voltage of the solution, then they read down the line, and what they would do then is they'd read the pH. Now, the middle pH meter is actually his second generation of pH meters, and actually this is the type that I would use when I was a student, and actually we first used it at Berg College. Now, notice that there's a readout that shows you pH. Actually, it's nothing more than a voltmeter, and the instrument itself will convert the voltage into pH for you. Now, I've marked 2 knobs I want to show you. This first knob is actually called the calibration knob or the zero control knob. And what you do is you put in a solution of known pH and then you adjust the E0. So you adjust it to what it's supposed to be. Now, the second knob is actually called the temperature control knob. Why is it called the temperature control knob? Remember that that 0.06 actually came about because of all of this is equal to 0.06. Okay, so R is the ideal gas law constant. Temperature, remember we decided that we're always going to work at 25 degrees Celsius. N is the number of electrons being transferred. That's a constant. F is Faraday's constant. Well, the reason this is called the temperature control knob is because you can vary the temperature, and what you do with that knob is it changes the slope, the direction of the slope.